All right, today I'm going to give you the notes for section 2.3 and 2.4. This is the defining and understanding parts of logarithmic function. And I'm going to give just the notes today, and then I will post another video that will have a bunch of examples that we do in another video. So the examples will come in a second video. This one is just the notes that we're going to use for logarithmic functions. So what I want to look at first, I'm going to just put out here a generic exponential. F of x equals b to the x. It has a horizontal asymptote at 0. And this we know is a function. It passes the vertical line test. This thing just continues on this way with an arrow over here. It passes the vertical line test. It goes to this point right here, which we all know this point is going to be called 0b. And it passes the horizontal line test. Because it passes the horizontal line test, then I know that this function will have an inverse function. There is an inverse, a reflection across the line, y equals x, over here, and that is going to be the inverse of this exponential curve. And when I do that, and when I flip it across this line over here, it's going to look something like this. It's going to come from down here, and then it's going to curve off and go this way. It will be the inverse of this, so it will be an F inverse. And we also know from inverses that if this point is on this curve, then this point must be B0 is on that curve. The exponentials all have a horizontal asymptote, so all of their inverses will have a vertical asymptote at x equals 0. So what is this inverse thing called? This inverse, so F inverse of x, is called, this was an exponential, this one is called a logarithmic function. That's what it's called. It's called a logarithmic function. We just abbreviate that to call it a log function. And here is our definition. So if x is greater than 0, why? Because that's the domain, x has to be bigger than 0. My domain, x has to be bigger than 0. If x is bigger than 0 and b is greater than 0, why is that? Well, because we can't have a negative exponential over here, right? Base number. And we know that b can't be equal to 1. Then we have this. Y equals the log base b of x if and only if b to the y equals x. This is the log form of a logarithmic, and this is the exponential form. Of a log. Well, how did this come about? Remember, this is a y, that is an x, and to find the inverse, I simply switch the x and the y's. So if I switch the x and the y of this function right here, I'm going to get its inverse right there. And that is the exponential form of a logarithmic function. This is usually how it's written. We want to be aware of this one because we use both forms in the process of doing stuff. Okay, so that is our definition of what a log is. If I give it to you in this form right here, it's the same thing as giving it to you in that form right there, and vice versa. So it is a log, and we put a little base number down here. The base number is basically whatever b is, the base. And then the x stuff is supposed to be in parentheses. Sometimes textbooks and things get lazy and they don't put the parentheses around this. This is called the argument, and it should be there. functions have some characteristics that we want to be aware of. Let's talk about those. So what are some characteristics of log functions? Number one, that all parent log graphs have a vertical asymptote at x equals 0. All parent log graphs go through the point 1, 0. Use this template to help you change between the two log forms. And I just use this little tip right here to help people be able to switch back and forth between the two forms. I try to avoid X's and Y stuff because it could be ugly and weird looking. So I usually give it, it's called the box, circle, triangle. Box with a circle equals triangle. And then you can change it either direction, this way or that way. And it becomes the log base box. Whatever was in the box there goes down there. And then of the triangles, whatever that is, goes there. And then the circle's over here. So basically the box, circle, triangle stuff. And we'll do some examples and practice this all out. But I'm just giving it to you right now. This is going to be your main thing. You really want to know this. You're going to use it in many, many different formats and ways in this unit. So you want to make sure that you know this little, being able to change forms. Okay? We use it in many ways. The thing to think about here is this. If I have this right here, see the circle is the exponent on that base. If you look over here, this entire log is the circle. So in a sense, the log is the exponent. It's the exponent. So we need to be able to remember that a log just means it's an exponent. All right, next. For a generic transformational thing, A times the log base B, and then I have to change this number in here is usually bx plus c or minus c. So I have, because I use b for the base, this will be kx minus c plus d. So you should be able to recognize this as your basic transformational format. So no matter what log equation I give you, from before over here, we talked about in the transformational form over here that the horizontal asymptote follows the up and down in the transformations. The vertical asymptote follows the right or left. So when I have it in this format like this, the vertical asymptote is when kx minus c equals 0. Solve that for x, and you will get your right or left shifts. And all parents start at 0. So if I have a right or left shift, well, vertical asymptote will shift with that also. Remember when you're graphing a log function that you use a dotted line, you represent the vertical asymptote, and you label the vertical asymptote. It's always an x equals, and it's required when you draw your graphs for me. So that's some characteristics that we want to be aware of. As we come across more, we can add to this list. Logs have some basic properties we want to talk about. These properties will allow me to simplify some expressions and things like that. So we want to make sure we know them, are familiar with them. So our basic beginning here, b has got to be bigger than 0, b cannot equal 1, and x has to be greater than 0. Your basic standard starts for talking about logs. The log base b of 1 equals 0 because b to the 0 equals 1. The log base b of b is 1 because b to the 1 is b. So if you want to know, so this little change right here, if you want to see the quick way of doing it, if you look at this right here, that's the base, that's the exponent, that's the answer. Base, exponent, answer. B to the 1 is b, that's why. B to the 0 is 1. What is log base b of b to the y? It's just y. Why is it just y? Because b to the y is b to the y. Base number exponent has to equal that. So b to the y is b to the y. Seems pretty straightforward. Another way to look at it is this. The log base b is the inverse of base b, the exponential, and so they cancel each other out, and you're left with just the y. Another way to look at it. This is like composition. I'm taking the log base b of base b to the y. So that cancels their out. So that composition, you're back with whatever this is on top. And this is the same thing, just in the other format. Log base b of x is just x. Because base b to a power, and that power has log base b in it, these two operations offset each other, and you're left with just the argument x. These are basic properties we use to help us solve equations, to simplify equations, and things like that. So we want to know these properties. Okay, the next thing I'm going to do is I'm going to turn the page over, and I'm going to give you some basic logs that are used. These are called, have special names, called the common log. And the other one is called the natural log. These, if you look on your calculator, are always the two buttons on the calculator that are being represented. Right here above the E, you'll see we have this LN called the natural log, and this one over here is just LOG for log. Now our calculator is more advanced, so some earlier calculators and scientific, low-end scientific calculators will only have those two buttons, and they don't do all bases. Our calculator will do any base for a log, so it's more user-friendly. But we will talk about some of those things here in a minute. What is a common log? It is log base 10 is the common log. That is what a common log is. It's base 10. We don't write it like this. Like many things in math, they like to use things differently. I can write it as log base 10, or if you see a log with no base written, that is base 10. It is the only log where you don't need to write a base number on. So if you don't see a base number written, it's base 10, the common log. The natural log, and a lot of times they'll use this lowercase l, and I don't like that one because it looks like a 1, and some people confuse it for like a capital I for some reason. I don't know why, but they do. So I use this, and this is log base E. So natural log would be a log with base E in it. They almost never write this If they write that, it's only because they're showing you this for the first time, and then they will automatically write it, and I use a lowercase cursive L, natural log, LN of X. Natural logs are always written this way, with a lowercase L and an N. I recommend you write it this way so that you do not get it confused with anything else. Why is it LN instead of NL for natural log? Basically because this stuff was done in Europe, French, German, Spanish, all put the descriptors after the object. So instead of like in Spanish, as some of you guys may know Spanish, in English we say it's the red ball, but in Spanish you do and flip that, and you basically say the ball, and then you tell me that it's red. So in Europe, same thing, where this math was developed, it's the same as Spanish, same kind of Romance languages, and so natural log, you define the object first, the log, and then you describe it as the natural log. So logarithmic naturalis is where it comes from, and that's why it's LN. It is not a capital I, okay? It's not a 1. It is a lowercase l for log and natural, okay? Please make sure you write it properly. That'd be greatly appreciated. And then we already kind of basically talked about the transformational stuff. So make sure you know that in logs, all the transformation properties still apply from when we learned it from before. Up, down, left, and right, you'll be asked to identify all transformations from a log graph. And just remember that the right or left is where the vertical asymptote will be. Now, let's talk about how to graph. This first unit here, 2.3, is about graphing, identifying logs, and graphing. First things first, all natural log graphs for all of those, you're going to use a calculator. Use a calculator on on my table. I'm going to show you how to make the table, and you can use the calculator then, just like when we did exponentials. You made my table, and then you can use the calculator to help you find the values of those numbers in the table. The same thing for the log. That's what I want. So how do I do this? You're going to change your log equation to exponential form. So we're going to change it from a log form to an exponential form. We're going to put it into this format. Okay? And then we're going to graph it using this format. And I'll show you how that's done. You're going to make your table. Be careful. You will be plugging numbers in for Y. And again, I'll show you some examples in an example thing. Follow the process for exponential graphing. Remember that you have a vertical asymptote, not a horizontal. You want to draw and label it as a dotted line. Make sure you name 2 key points. And name the graph if it's not sitting there already. So again, a bunch of examples are going to come in the next video. Right? That's what we're going to follow though. That is what I want to talk about in 2.3. In section 2.4, we're going to learn how to do some simplification with some log stuff, some properties, more additional properties of logs. I'm just going to give those to you now. And we use these to help us simplify our work and stuff like that. So here's the rules, and you want to make sure you know them. They go beyond this class into the next class. You'll need them in the next class also, so make sure you learn for a longer term period. Expansion and condensing rules for logs. This is the product rule. If I have the log, base, whatever, and then a product inside the argument, I can split these 2 products apart as 2 separate logs. So this can be log base u, log base b of u plus the log base b of v. So I can split that product apart with addition. The quotient rule. And I can split that apart in this fashion. The top one minus the log of the bottom. The third one and last one is the power rule. If I have the log base b of something to a power, I can take that exponent right there and multiply it out in front of the log, and it is the same. Just like so. So expanding would be taking something like this and expanding it apart. So using the rule in this direction. Condensing would be going the other direction. Condensing it would be going from this to that. Recognizing I have that and writing that and so forth. So condensing is going this direction. Expansion is going that direction. We will use these quite extensively. Another rule that you need to know, I mentioned this kind of like some calculators do not have the ability to do every base. So you would need a change of base form. Our calculators will allow us to type in log base 3 of a number, but not all calculators do. So since you can't type in a log base 3 into other calculators, you need a way to change it because all calculators will have the natural log button and they will have the common log button. They all have that. Ours just has one that does all bases. So that makes it easier. So how do I put in a log base 3 into a calculator that doesn't allow me to put in base 3? You have to do a change of base formula. And the change of base formula simply says this. I have 2 variables that can't be equal to 1 in both cases. Log base b of x. So any base I have can be changed to any other base you want by this formula. Log base a of x divided by the log base a of whatever the old base was. Since I can change it to any base that I want, I can make a base 10. Or I can make this log base e as a natural log. Most of the time what we do is we just change it into the natural log of x divided by the natural log of b. Or we'll use log base 10 of x log base 10 of B. So usually for calculator usage, we just type it into one of these two forms. But know that I can change it to any base I want by this formula right here. And that's what we're going to be practicing in 2.4. So with that, that's the information. And now we'll start doing some examples.